This video is the final part of a series reviewing my dissertation, Results in Atmospheric Waves. Today we will talk about the final chapter, Extratropical Excitation of Equatorial Waves. Now we have spent the past few videos talking about what the Matsuno modes are, their behavior on larger scales, and instability arising from meridional circulation. Today we will discuss one way that these waves might arise in themselves before any of these other modifications. We begin with the linear equatorial shallow water equations, but now we have added a bunch of forcing terms in yellow. These forcing terms are configured so that they move along a line of latitude y equals a at a speed s, where s equals 1 corresponds to about 50 meters per second in the eastward direction. For a given forcing configuration, a lot of Matsuno modes respond, but usually only a few will have the largest response, with a very quick drop-off after that. We know this by a big matrix inversion in an appropriate basis. Technically, we can get analytic expressions from these, but they are for the most part quite complex. Nonetheless, we can make some qualitative observations of what excites particular modes, and to do so, we'll consider the simplest of these analytic formulae. The simplest case is that of the Kelvin mode, which is written here. The other expressions, while more complicated, are most influenced by these same four factors. The most important one is how much a forcing resonates a wave. If you've ever seen videos of bridges wobbling when people walk on it the wrong way, it's the same idea, except we express it using velocity, which is okay since velocity is proportional to frequency. Next, particular forcings trigger particular waves, some not at all. It is important, but unsurprising. After that, the meridional location of forcing influences responses. If the wave isn't resonating, then it had better hope that the forcing is nearby, or else it won't be excited at all. If there were no damping, a forcing moving at speed s equals 1 would cause an unbounded response by a wave. Here we have an XY picture of how a forcing can excite a Kelvin wave, with the arrows being the winds over the height perturbation h in color. It is moving at y equals 2.5, x equals 0, with speed s equals 1. The green and blue blobs near y equals 0 are the different phases of the Kelvin wave. We also see a response near the forcing which is stronger. But this example goes to show that the resonance can still excite a wave, even though it is thousands of kilometers away. This slide is the same as before, but we have moved the forcing closer to and away from the equator on the left and right respectively. The left wave has a much stronger response than even before. While we still see a response on the right, it is dramatically smaller. This slide has moved the forcing back to where it was on the first slide, but we have slowed it down. Now we see a response that looks Kelvin-like, but it is weaker and offset from before. Now we have examined other settings, but a different damping or forcing configuration doesn't qualitatively change much beyond the amplitude. Rest assured knowing that our formula does track the Kelvin response. Now there are many effects that can force this system, but we decided to understand the effect of interaction with barotropic modes. The result is a simple extension to the shallow water equations, and we can analyze the same moving forcing structure on that equation. This problem cannot be so easily reduced to a matrix inversion as before, but it does lend itself to a pair of Green's functions that depend on the direction s and produce different spatial structures. Getting back on track, there are a number of interactions between the barotropic modes and Matsuno modes that excite other Matsuno modes. One example is how the barotropic mode can interact with the EIG mode to produce a Kelvin wave by way of a forcing moving at speed s equals 1. With that, I would like to thank you for watching this and all of the videos in this series. If you have liked this video, then please like this video. I might, and I mean might, make more math videos on YouTube. So if you subscribe to me there, you'll get them as they come out.